So we're going to talk a little bit about applications of quadratics. And in section 12 of Alex, the first few problems have to do with optimization. And actually, optimization is used in a lot of different areas, a lot of different maths, and business in particular. Here's kind of the general idea. So as you can see, you can see how this could be a parabolic or quadratic shape. This one would be upward facing parabola. This would be a downward facing parabola. And because they have a minimum or maximum value, they can be used to understand where that occurs, right? And in particular, a situation where you might need to do that is where you're trying to minimize costs. So you're trying to keep, in a business, you might try and keep your costs at a minimum. And if you think about it, as you sell the number of things, we'll call them units, right? And you sell, the first few that you sell are really expensive because you have all that R&D and stuff, and you're getting your machinery together and all that, and you're paying a lot of people. Then and it gets really expensive, and as you sell more and more and more, up to a point, you will minimize your costs per unit. And then beyond that, if you start making more and more and more, then sometimes your expenses can go up, where you have to pay more people to make that unit, to make those different things. Or you might have to buy more machinery, or you might have to build another factory. Okay, so most businesses have a sweet spot where where their costs are at a minimum for the number of units that they're selling. Another way to think about that same situation is profit. So as initially your profits are quite low, and then as you sell more units, they go up, and then once again those costs start mounting up, and so then your profit per unit goes down. Now if we look at this parabola, right, there's lots of ways that we could write it, but the key to it is once again that leading coefficient, right? So in this case, my leading coefficient is going to be positive, right, because it's an upward facing parabola, okay? And in this one, my A, or my leading coefficient, is going to be negative because the parabola is facing down. And that's kind of one of the ideas that we're going to use again and again in these first few problems. So looking at these word problems involving maximums and minimums, right? Let's take a look at what's going on here. A ball is thrown vertically upward after t seconds. Its height in feet is given with the function 40t minus 16t squared. What is the maximum height the ball will reach? So once again, this is a maximum problem, and so we're going to be finding the vertex. Okay, so let's switch back over here. So h of t equals negative 16t squared plus 40t. Okay. Now, and you can see that this parabola is going to be going something like this, fairly steep, because that leading coefficient, is negative. Okay, and we need to find that vertex. Okay, some of the book often talks about the opposite of b over 2 times a is the coordinates of the vertex, and in this case, completing the square is going to be a little bit awkward. Because 16 doesn't go into 40, so we'll use this method. So in this case, my b, the x-coordinate of my vertex, is 40, and all over 2 times negative 16, right there. And we do some math, and we get 40 over 32, which if we do some magical math stuff, and I'm going to get 1.25. Now that's the x-coordinate of my vertex, right? Now let's look and see what the question is asking. Okay, what is the maximum height of the ball will reach. So in looking back at this, how does this value can help us out? If I know the x coordinate of the vertex happens at 1.25 seconds, right? Well, how can I find that height, that y value that goes along with that? Well, I can plug it in right into my formula. So I can say h of 1.25 equals negative 16 times 1.25 squared plus 40 times 1.25. 25. So the maximum height occurs at 1.25 seconds, and it is 40 feet in the air.